Hello. Thanks for jumping on. Very much appreciated. This stream is actually a repeat, not really a repeat, it's a redo of a complete disaster that I tried last week. Basically, last week I tried to do the exact same thing, which was take some audio and transcribe it, so pull the text out of that audio using Google Cloud, and things did not go well. Actually, to the point where I did something I almost never actually do, which was pull down the stream because it really wasn't useful. It wasn't going to be useful for anybody watching in the replay because you didn't really learn anything other than seeing a middle-aged builder get super frustrated. So here we are again. We're going to tackle it out. I've changed things up a little bit. I want to try some things. Getting back into the swing of this live coding and streaming and engaging with you live. So if you have comments, drop them there in the YouTube comments and I will address them as we go along. But I'm going to switch over to my other display and we'll see what's rocking here. All right, there we go. So what we've got here is a different way of approaching it. And I gotta tell you, I cannot understand why I did not think of this before. Instead of flipping back between a command line and my code editor, I'm actually just gonna do everything in the browser. I fired up Jupyter Notebook to go along with this. And I'm sharing this out on the GitHub repo, and I'll ping that to you guys after in the chat. But basically what I did was install this really straightforward. I have the instructions in the repo if you wanna do this yourself. Install Homebrew, install Python 3, install Jupyter, and you're good to go. Jupyter just gives you an easy way of sharing text and executable code in the same document, in the same notebook. And you can pass these around. There's some really great tools like the Google Collaboratory. There's some great ways to run this on AWS. I'm sure Microsoft's got something. I've never looked into it, but really it gives us an interactive way to walk through this. So let me switch over to this tab, and this is the project setup. Now I want to tell you what I've already done. Just going to verify that things are rocking, and it looks like they are, which is great. So set up the project. I've installed the Google Cloud SDK because we're using Google Cloud to do this today. Similar service exists on AWS and on Azure that you could use as well. I found more success with Google, and I had a bunch of code already written to handle this kind of scenario previously, and a bunch of stuff from the failure last week. So this is what we're using, but again, the same concepts exist. But what I did was I pre-installed the Google Cloud API, and then I took us 2 steps further and installed the specific Google Cloud speech section of the SDK. Remember, the Google Cloud SDK comes in chunks when it comes to Python, and you need to explicitly enable each set of services. And I actually enabled those in my Google Cloud project as well. Every API in the Google Cloud is disabled by default. You need to explicitly enable it. I saved you that step. I went through and did that. Now, the good news here is to remember, if you forget to do that, when you run your first request, that's actually in the error message. It says you forgot to turn this API on for this project. Here's the URL to go do that if you have sufficient permissions. Also, I added my Google Cloud credentials into the environment variable that's running the Jupyter Notebook already. So that's in play. So basically what I've done is I've pre-configured the environment so that it is the optimal to get us rolling and let us actually learn and explore this particular API. Last thing I wanted to call out was the file formats. Now, this is something I stumbled over big time last week, even though I've dealt with this API before. It is very picky about the type of audio that you send it. I wish this wasn't the case. I wish you could send it anything and it would do the work for you. Not true. You have to do the work yourself. So there are a number of ways to tell it what type of audio you're going, but realistically, if you send it mono wave files, you're going to be good. And to do that, you could do it within Python. I think it's a lot easier to do it with FFmpeg. That's a utility that runs in Linux and in Mac OS. There's equivalents in Windows, and actually you can run this one in Windows now with a Unix subset. But I've also put the command to strip out a single channel audio out of any file, including video files, in this Jupyter Notebook. So if you had a video file, which I use quite often to do transcriptions, you can run this command in FFmpeg, and it will pull out the audio from the video file, which is much easier to work with because you don't need to process the video through this API, just the audio. So you're actually going to get a smaller file, which is great. So first things first, and this is the beauty of these Jupyter Notebooks, is that we need to import the SDK. In this case, what we're doing is we're importing the various pieces. I was using some of the beta stuff. I don't think this is actually required anymore. So we'll take a risk here. Okay, we need to import speech because it's now v2 of the speech, and storage. The reason why we need storage is because for audio files that are longer than a minute, you actually need to take them from Google Cloud Storage instead of sending them directly to the API. So we've got two major pieces here. We've got speech and we've got storage. We're going to run that code. Everything works as expected. I now have 3 sample audio files. I've got an MP4 audio file, I've got a short WAV file, and then I've got a longer WAV file that we're going to use all 3. So I'm going to run this code block to create a little array of file paths. Very simple, very straightforward. And you see why I really am kicking myself that I didn't think about Jupyter Notebooks before. This is super simple. I can clearly comment the code. This top block is actually a markdown block. Makes it really easy to follow along. And then you execute each in turn, and it shares the context throughout. So you can refer to the variables up here, down here. Gives us the same ability as the Python interpreter, but in a much nicer way to walk through in these kind of demonstrations. Just if you're wondering why I'm looking to the left, I got the dually screen set up. I got finally a nice big screen that I can read easier here on the second cam, but I got all my streaming stuff on the first cam. So if you're asking a comment, I just want to make sure that I've got it and I can pull that up in the broadcast. Also double checking the volume and making sure the broadcast is nice and healthy. So we've got our sample audio files, the path to those in an array that we can refer to. And the first function we have here is really just a straightforward one. This uploads a file given a path to a Google Cloud Storage bucket. Very easy. And what it does is it returns the Google Storage URI, or Universal Resource Identifier, which is what we need to pass to the speech to text API. So essentially we're shoving a file in a bucket and we're getting the address of that file in return. So this function, very, very simple. It makes sure that the local file exists. If it doesn't, it just returns nothing. Then we create a storage client. We get the bucket according to the bucket name. Then we get the base, the file name from the file that's passed, and then we get the data from the file. Very simple. So we get the blob file name and then the blob itself. Then we upload it. Real simple. We print our return that, hey, we've uploaded this file to the Google Cloud Storage bucket, and here is the Google Storage URI. Very, very simple. We're going to run this to put the function available in memory. Now we're going to leverage that function. The Google Cloud SDK makes this super, super simple. You can see that code is 24 lines with some nice formatting, with some nice error handling. What we're going to do is we're going to iterate here now through our FP samples. This is the file path of our sample audio files. Again, this is all going to be in the repository. And we're going to upload those, and we're going to record the Google Cloud Storage URIs into a similar array. So GCS, so Google Cloud Storage samples. We're going to create all of the Google Storage URIs there, and we're going to print those out. We're also going to return that. So if we click that, you're going to see we get our first outputs. Uploaded this sample file to Google Cloud Storage bucket, TCP's Tiny Cloud Projects data, and then we get these Google Storage URIs in return. This is what we need to send to the speech to text API. So what we're doing here is, instead of trying to evaluate how long our file is and decide to send it directly or to use Google Cloud Storage, we're just simplifying our process. We're putting all of our audio files into Google Cloud Storage in order to then send them to the speech to text API. Because we have them in a simple array, we reference that array here, and we can just change the number in the array, the index in the array, to get the file that we want to send. So we can send a couple different samples through to see how the API reacts. But this is our code that does the meat of what we want to do. And we're going to dive into some of these after we see a quick example of what's going on, because there is a really, really important call out that's probably just the bulk of what I want to tell you about this API. But we create a client for the speech client. Then we create a recognition audio, an audio sample. And this is telling Google Cloud where the file is. And then the critical aspect here is in line 3. It's the recognition config object. This defines what we want out of the API, but also our how our data is formatted. Now, this has changed a lot from V1 to V2. Now in V2, it's much more robust. It makes a lot more sense. And a bunch of these options that were hidden a year ago are actually in play now and clearly documented. And I will show you that in just a second. Once we have the configuration, so we've got 3 objects here. We've got the client for the speech-to-text API. We've got the audio file. We've got the configuration of that audio file. Then we can run the operation. So here what we're doing is in line 11, we have the results. We keep that as none so that we can easily test those results. And then we put it in a try catch or try except block. We run the operation, which is a long running operation to recognize. That's what this is called. So the client is the speech to text client here on line 13, and we are calling long running recognize. So recognition call, but it's going to be long running because we're not sure if this is a short audio or a long audio, and this could take a while. And that's exactly what we've got here. So we're going to print out a friendly warning and say, hey, wait a minute, this could take a while. Because the longer the audio, the longer the transcription takes. If you send this an hour, it's going to take 3 to 5 minutes ballpark, depending on what's going on, to give you back the results. So in this case, we give it a specific timeout of 3,000 seconds, and you can increase that or decrease that. You could also do this through polling. So right now, what we've got is a blocking operation. What that means is when we run this chunk of code, it is going to stop execution and wait for a response back from Google. So if you've sent it 2 hours worth of audio, your code is going to be sitting there occupying that process for quite a long time. You can do this asynchronously where you send it and say, I'll check back later, and then you come back in and check it later. And by default, that's actually how the AWS API works, which for most use cases, especially if you have a user interface, that's what you want. You don't want to block your user interface. You don't want to block things while you're waiting for this response. For what we're doing today, it's no big deal. Once we get the results, we capture them in a variable shockingly called results, and we're going to print them out. So we're going to start with the first sample. Now, the first sample, if you'll remember correctly, is an MP4 audio file. Now, this is going to freak out. It's a short audio file, so we should get a response very quickly. We're going to run this piece of code, and you'll see right away we are getting we got an error, is that the no attributes type. So I'm using an old version here. Remember in previously we commented this out. We're going to comment it back in. I'll save that and I'll rerun that top chunk just to make sure. And then we go back down, and this is what I get for copying some code over from a previous beta, in that I need to clean that up purely for V2. But now let's rerun this and we'll see what happens. So right off the bat, we get a response and it says, could not transcribe audio file through exception 400, invalid recognition in config, bad encoding. So if we go back up to our line 3, you'll see we have a recognition configuration here. This is not telling the API what this audio file is formatted as. It's saying, I was expecting something else. What I got was this compressed MP4 audio, and I don't know how to handle it. In fact, if we flip over to the documentation, almost, you'll see that we have an audio encoding enum in here, an enumeration for audio encoding, and you can actually specify what types of encoding your file is. And you can see it not specified is it's going to do its best job, which is what by default we're sending through there. Linear 16 is a WAV file. FLAC is an open source codec, which works really, really well. Moolah, ARM, OGG, SPEX. So there's a bunch of different formats. Odds are you're going to use linear 16 almost all the time, or just not define it and it will figure it out. It's linear 16. This is what I found to be easiest, is across the API just to use WAV files. Just use mono channel, so not stereo, mono channel WAV files. Makes life a heck of a lot easier in this recognition config. You can go further to say, hey, no, it's actually 2 channel. So you can say, instead of doing it down to there, and you can actually go and say there's separate speech on each channel. So this is common in scenarios where with like a Zoom audio recorder, on one channel, left channel is me, and then on the right channel is the person I'm talking to. So you can actually put that in there now, which is nice. That never used to be available. We're going to come back to this in a second, but I want to show you the results. If we change our file to the actual WAV file, so now we're going to send it a 16-bit mono channel WAV file. If we rerun this, it's going to wait for the transcription operation. You'll see right away now it's actually taking time to do something, whereas before what we saw was an immediate, hey, I don't know how to deal with this file. So what happens is we get all the response back. So let me just scroll down a little bit here, and you see we get this structure back as our response, this nice structure of all these different things. So alternatives, we get this is a test, 1, 2, 3, 4. We'll Google Translate all of this or transcribe all of this, which is something I always mix up. That's the contents of my audio file. And then we get a overall confidence, and then a breakdown of each of the words and when they occurred. Now this is really important. We're going to get into this in a second, But this is a clear success, which is always nice. We have a success right out of the gate that we've properly transcribed this audio, and it's working for us. Now, let's dive into what we actually got back in the response, because if we ask for different things, if we remove this one, we remove automatic punctuation, and we remove that, we're going to have to add in another bracket here. But let's rerun this code now, and you'll see that our transcription results are going to be significantly shorter because we haven't asked for specific offsets from the word. So it's not going to tell us when each word occurred. So you'll see now we get a very different return. I don't even need to scroll through the block, the return block. I just get a straight transcription. Here's the entire text, same thing again, with a confidence and a language code, no other timing information. This may be exactly what you want. Okay, and this is a great way to customize what you want to get back. And if you just want to get the text back with no additional utility to it or no additional structure, that's great. That works fine. For our cases today, there's actually a reason why I asked a bunch of this. And now I'm going to flip over back to the Google Docs again. And we're going to rerun that in a second. We'll ignore it. But the recognition config is where we define these items. We already talked about encoding. So the first three items here: encoding, sample rate, audio channel, different separation per channel. Those are all about the file you're sending the API, and you're telling it about that file so that it doesn't have to try to guess these things. The next you get is more about the speech. So what language is it happening? You can actually preset that so that it will use that in the transcription. So for a lot of the time, for me, in English US is fine, but I may actually want to put that to Canadian English or UK English so that it returns the proper spellings of words like favorite and others, so that I get the U's back, because as a Canadian, I very much value those U's. You can also have it filter out profanity. You can provide various alternatives, provide some context. So that's telling Google about how you want them to treat this text and return it back to you. Similar with the enable word time offsets and the automatic punctuation. That is the offsets is going to tell you that at 30 seconds in, this is when the word next was set. So it'll give you a specific time per word, which is very important to one of the use cases I'm going to show you in a second. And same with the automatic punctuation. It will try, based on the context, based on the tone, we'll try to add the proper, question mark, an exclamation, period, that kind of thing into your text for you. Commas for pauses, things like that. Very useful, very, very handy. Diatar, I can never say this word, so I'm not even going to try, but the speaker config basically tells you, you can tell the API how many speakers are in here, or how many speakers it should be looking for, as well as whether it should be trying to figure out which speaker said what word. And so that will then return within those results saying speaker 1 said this, speaker 2 said this, with the confidence level, because it's not always spot on. That is something very, very handy. And then there's some additional fields for metadata. I'm not sure what it is. That's a new one. Let's scroll down and see. Metadata regarding this request. So microphone distance, original media type recording. So literally metadata about the audio file, so that you can have that for your records, and then the model of what you want to be using. So this will help them apply the correct machine learning model. So whether this is voice commands or voice search, so short little queries that are structured not necessarily in native English. If you've ever tried to interact with the Google Assistant or Siri or Alexa, you would know that we speak differently when we speak to those, so you can use that model. A phone call, which is basically crappy audio, that's very handy for more situations than just phone call. If you have a bad recording, that's a great one. Video is for when you've got multiple speakers or it's coming from a higher quality thing. It's also a premium model, very important. This little bit here, it costs more than the standard rate. And we'll cover pricing in just a second. And then the default. And then so you can also use enhanced, which is another improvement on top of it, trying to go a little bit deeper, and that takes a little bit longer to process. So that's all within the config. The recognition config here on line 3 is essentially telling Google, here's how I want you to process this request based on the audio file, based on how I want the results back, based on the situation in which this file was recorded. Play around with it to get the best results for your particular situation. So we've rerun the results. We've got our longer transcript back, and it comes back in this nested set of dictionaries, and it's kind of a pain in the butt to navigate. So I've actually created another function, this one called parse transcription results, that takes the default results from the API, and from there it then formats it in a way that I find much easier. I'm going to adjust the time codes to unify them out to get the time at when each word started and when it didn't as seconds and as milliseconds, the total duration of a word, and then I'm going to append that in a structure that makes it easier for me to then use in other cases. So basically I'm taking their big chunk of nested dictionary results and I'm formatting it into a couple very useful lists. I'm doing just full text, so just straight default text. I'm doing it in segments, and I'm doing it with timing as well. The reason why is because then I can use that to create a captioning file. I also have this handy little function called getTimeCode that takes a time code in milliseconds and returns it in a nicely formatted hours, minutes, seconds, and milliseconds based on the time of the file. So let's run that code to get those functions available. And now I just take the standard results here in line 1 in this block, the results given to us from the API, and I'm going to put them into a new variable called structured results that have gone through this process. That should work. It does. Very handy. And now I'm going to print out the timing results just to show you what those look like. So you'll see here now I get a dictionary that says, word this, just as this is the first entry. So it's an array of these dictionary objects that has the word, the time code start. So this started at 6/10 or 6/100,000ths of a second. And then it finished at 1.1 seconds. And it was a half millisecond, or 500 milliseconds, sorry, in duration for the word this. If I print the next, if I go to the next word and we run that, you're going to see the next word was is, and it took 100 milliseconds. So that's what I've done with those structured results, is I've taken that big blob of sort of really hard to navigate, and I ran it through one function to give me back more structured text or more structured data, more logical data structure, so that I can actually navigate it easily. And this is where I think that's really going to click in as to why I would possibly do that. Let me just double check to make sure. Yeah, we're still doing good here. Awesome. Okay, so the reason why I did that was to create an SRT file. So a subtitle file. This is what YouTube wants. This is what LinkedIn wants. This is what many places where you're posting video wants as a subtitle file. And even my editor in Final Cut Pro, I have a Caption This plugin, which is really great. Awesome investment, and it's really paying off. But it wants files in this format, and that format is very simple. It takes a number at the block, so 01, 02, 03, the time code at the start, then the space, then a dash arrow, space, time code at the end, then all the words. So we are going to build that out based on that structured result. We're going to go through all the word timings, which are an array that we already have in place, and based on the desired line size, so the default's to 35 characters per line, we are going to generate a SRT file that I can then use as captions. So all of this code here, looking at line 10 through line 31, just formats all of that structured result into the desired SRT format, which is time code start and end with the actual file in a numbered set of blocks. So we've got that. We'll run that in place. And here what we're going to do is we're going to say, okay, we'll do it really short. We'll do the default, which is 35. We'll generate the SRT and we'll see what happens. Ooh, I got an error. So generate SRT is not, let's run that. There we go. And then run it now. There we go. Okay, it just hadn't run that code block. So with Jupyter, you have to run every code block, unlike a normal Python file where if it's in the file, it's fine. You have to run each of these blocks. We need to declare the function to get them pushed into the interpreter so that you can then call them back. So here's our SRT file. Very simple, very straightforward. This is a test. This is a test 1, 2, 3, 4. 4 comes on the next line. So this would be the next set of captions that were displayed on the video. And it's just perfectly lined up. So if I said, if I go down to a line size of 10 and then run that, you can see this is a smaller line size. This is a test, and it gives us the appropriate block length. So depending on how fast you want your captions rolling, you're going to regenerate, you're going to adjust these line sizes. 35 seems to be about reasonable, but I do use smaller line sizes when I'm doing a vertical format video for short. So that's how that works. That's very straightforward, very simple. What I'm going to show you is how this works with a longer file. So this is going to take a little bit longer. We're going to actually go to the last one in the array, and we're going to run this back out. And you're going to see this is going to take a little bit longer because now we're sending it a file that's about 3.5 minutes long. It's me reading a couple articles. And again, this is why you want to be very aware of what we're doing here in this block in line 13. With a long running operation, we're actually locking that thread that's running that code because we're doing it in a synchronous manner. You can do an asynchronous call. That is an option through the SDK. But very simple, very straightforward. While that's going, what we're actually going to do is we're going to go over here and we're going to go to pricing, and we're going to look at the price list, and we're going to find the Google speech to text API, which is part of the AI vision blocks, building blocks, sorry. And you'll see here our pricing table is very reasonable. Up to 60 minutes a month for speech recognition is free. And after that, for every 15 seconds, up to 1 million total minutes processed, you're going to be paying 6/10 of a penny for 15 seconds. So, you're looking at 30 seconds for just over a penny. Now, if you're using the enhanced models, which is the video mode and the phone call mode, you're going to be paying 30% more, so 50% more, sorry. So 9/10, almost a full penny per 15 seconds. So keep that in mind. And then you'll see, I really do like this, the pricing factors, whether recognition is performed using a standard or enhanced. Whether you've opted to do data logging, and the number of channels being being recognized. Essentially, the channels, if you send it and say, hey, stereo, we're processing them both, that's going to double your processing time because it's looking at the left channel for 15 seconds and the right channel for 15 seconds. So it actually counts as 30 seconds. So something to be aware of. But for most people, you're probably not doing more than 60 minutes a month. And if you are, it's quite reasonably priced, quite competitively priced. And the other APIs from the competitors come actually in line with that. So it's quite reasonable count. Now, when we switch back to our notebook, we've got our longer audio file in play here. So I'm going to scroll down, and we need to run this guy. We need to rerun the structured results. And now if we look at the timing, yeah, we should be okay. So let's generate the SRT for the new results and see how this goes. Okay, so we got a much bigger text file, but you can see now we have new text. This is an article called Updates on the Twitch Security Incident posted to the Twitch blog. This is our first error. This is not the end of a sentence break. Okay, now this depends on the cadence of the speaker. It depends on the model you picked. We picked the default model, so we're not paying more. And so it's getting the wrong end of sentence. So you do have to review these files. You can't just use them in production right off the bat. But this is a pretty, it's got the words correct. It just has the capitalization and the end of the sentence incorrect. Keep going down and you'll see this has all of our text, and we scroll. You'll see near the end, I'm just gonna get to the end here. Almost 4 minutes. Done very quickly, very simply, very straightforward. And this is generating a subtitle file that we can then use in whatever we want. So if you want to upload this to YouTube and have the chance to manually review as opposed to YouTube generating the captions for you automatically. If you're posting on LinkedIn, this is the file type that you want. Again, I'm going to post these up to the Tiny Cloud Project GitHub repo, so you can see all the code here in the Jupyter Notebook. I'll save it to make sure we've got the latest one. And let me flip back to the main camera here. And that's it. Very simple, very straightforward, way more successful than the last time we tried to stream this. But you saw very quickly within 20-30 minutes here, we were able to send multiple files up to the Google Cloud speech to text API, get the text transcription back from those files, and then convert it into a more structured, more reasonable set of results as far as the data structure goes, something more logical than just a nested dictionary of dictionaries of dictionaries. We created some of that logical structure for us to better process it, and that made it much easier to create those subtitle files. So within 100, 150 lines of code, we were able to take that audio and get a finished subtitle file product back. And that's easily repeatable. It's very quick. If you're doing it for less than an hour a month, that's free, and it's very inexpensive afterwards. And that's the power of some of these cloud APIs. And that's really the goal of me streaming this kind of stuff. It's fun for me to build these these fun little utilities, but also a great reminder that you don't have to leverage cloud to build only massive, huge things. There are these little lifesavers. Like if you're just trying to get transcripts back, very simply get the computer to do the lion's share of the work, and then you can manually review it to make sure it's actually correct. That is a lifesaver. That 5 minutes of processing time could save somebody an hour's worth of work, very, very simply. And that is a great tiny cloud project. Thanks for joining me, and I hope to see you